Welcome to The Explainer, where we break down big ideas. Today, we're diving into something huge, a claim that could literally rewrite 2 centuries of mathematical history.
So, what if a mathematical impossibility, something we've just accepted as fact for 200 years, was all just a big misunderstanding? Think about that. For 2 whole centuries, a specific kind of math problem wasn't just considered tough, it was proven to be impossible. And now, a mathematician is claiming they've solved it. It forces us to ask a really wild question. What if it was never actually impossible to begin with?
Okay, to really get why this is such a massive deal, we have to rewind a bit. We need to look at a super famous problem in algebra that has been a thorn in the side of the greatest mathematical minds for centuries.
Now, you've definitely seen these before, right? Polynomial equations. They might look like just a bunch of letters and numbers from high school math, but they are everywhere. Seriously, they model everything from the arc of a thrown ball to the chaos of financial markets. They are the absolute bedrock of how we describe the world mathematically. But here's the catch. Finding their exact answers, what mathematicians call their roots, gets exponentially harder the more complicated they get.
I mean, for a long time, we were making amazing progress. You probably remember the quadratic formula from school, right? That cracks any second-degree equation. Then, back in the 16th century, these absolute geniuses like Cardano and Ferrari, they figured out the 3rd and 4th degrees. It really seemed like they were on a roll, just knocking them down one by one. But then, they got to the 5th degree. And they didn't just slow down, they hit a solid brick wall. And this wasn't just any wall, it became a boundary that would end up defining what we thought was even possible in math.
So let's talk about that wall, because it didn't just stay a mystery. It became a fundamental law of mathematics. This wasn't a temporary roadblock. It became a core principle of what was considered solvable.
And that brings us to 1824, and a brilliant Norwegian mathematician named Niels Henrik Abel. He's the one who proved something that was just astonishing at the time. He showed that there is no single universal formula that can solve all polynomial equations of the 5th degree or higher, at least not using the standard tools of algebra, addition, subtraction, multiplication, division, and taking roots. And when you see it laid out on a timeline like this, it's just wild. You see this incredible arc of progress stretching over millennia. Degree 2, boom, solved. Degrees 3 and 4, check. And then in 1824, everything just screeches to a halt. For nearly 200 years, that was it. The problem was considered a closed case.
And this is the part that is so crucial to understand. It wasn't that mathematicians just weren't smart enough to figure it out. The theorem was seen as definitive proof that a general solution of the kind they were looking for was logically impossible to create. That idea defined the limits of algebra for generations.
But what if the problem wasn't the lock, but the key they were using to try and open it? And this is where our story takes a really dramatic turn, with a modern-day challenger. Enter Professor Mourad Sultan Ezouidi. He looked at this 2-century-old barrier and saw not an absolute truth, but a limitation of a very specific framework. He basically argued that Abel's proof was correct, but only within the confines of 19th century methods.
And this table just lays out the heart of his argument perfectly. Where the classical methods hit that wall, his theorem claims to achieve exact symbolic solutions. How? By ditching the old theoretical basis and using something new called recursive discriminant structures. Now, I know that sounds complicated, but think of it like a set of Russian nesting dolls. His method opens one layer of the problem to reveal a simpler one inside, and then it does it again and again until the answer is all that's left. And that's how you leap from numerical approximations to a 100% verifiable algebraic answer.
So, the billion-dollar question, right? How does this supposedly work? How do you solve the unsolvable? Well, the answer seems to be thinking completely outside that 19th century box. See, his theorem doesn't even try to create a single massive formula like the ones that came before. That's the old way of thinking. Instead, it introduces a whole new process, a structured procedure that lets you unpack the equation in a way classical algebra never could. At its core is this recursive or repeating process. First, the method finds hidden patterns inside the equation's structure. Then, it uses those patterns to transform the problem into a slightly simpler version of itself. By repeating this simplification over and over, layer by layer, the equation essentially solves itself, until the exact roots just pop out. It's a completely new way of thinking about the problem.
So what this really means is a huge shift. Right now, computers give us answers that are super long decimals. They're really close, but they're still just approximations.
Ezouidi's claim is that his method gives you the perfect, exact form. Think about the difference between saying 1.4142 and so on, and just saying the square root of 2. One is an approximation, the other is the exact truth.
And here's the proof in the pudding. Professor Ezouidi's paper presents a complete symbolic solution for a 9th-degree polynomial. Let that sink in. Not the 5th, which was the original wall, not the 6th, the 9th degree. That's a level of complexity that has been firmly in the land of impossible for 2 centuries.
Now, if this groundbreaking work holds up to the intense scrutiny of peer review, the implications are absolutely massive, and they go way beyond just solving one type of equation.
This discovery really attacks a core belief that some problems are just fundamentally beyond our reach. It suggests that what we see as a hard limit might just be the edge of our current toolkit, the boundary of our current perspective.
Ultimately, what we're looking at is a potential philosophical shift. It reframes a historical endpoint as a brand new starting line. It suggests that, with the right perspective, maybe no equation is truly beyond our reach.
And this might be the most profound takeaway of all. The achievement here isn't just about finding an answer. It's about changing our very definition of what is answerable. It's a potential transformation in how we understand mathematical truth itself.
Which leaves us with a thrilling question. If a 200-year-old impossibility can be overturned just by a new way of thinking, what other walls in science and mathematics are out there just waiting for the right person to come along and show us they were doors all along?